We're going to do a review. I hope everyone knows there's an exam today. Did you all study yet? Yes? Somewhat? Okay, there's time. There's time. The exam is today. I heard somebody say really. It's 7 to 9 p.m. Yes, really. Okay. And, you know, there's some logistics here that would be really helpful to the grading process if you just listened up. When you do the Scantron, you need to fill out your student ID number. Yes, there are more little slots than there are digits in your student ID number, but you start on the very, very, very left-hand side. You fill over and you have 2 empty boxes maybe, or 1 empty box, whatever it is. Leave them blank. Do not put zeros there. Putting zeros there means that the exam has to be manually dealt with, okay? And every time you have to manually do an exam, it adds another 2 or 3 minutes to the grading process for all those. And apparently it's becoming, it's fairly common for students to want to enter in zeros. Don't do that. And the other thing that you'll need to do is you'll need to do a couple things for the exam to be scored properly, and that's indicating the form of the exam, which is Form A. There's a little box for that. You have to fill that in. Again, that will reject your exam during grading. And all these things lead to, you know, clerical errors. So, you know, if we can minimize that, then we'll have fewer clerical errors during the grading. That's the main issue. The exam's 40 multiple choice questions, 2 points each. It should only take you 45 minutes. It took Beatrice and I about, you know, I don't know, 20, 25 minutes to take the exam. I know we designed it. That's not very fair, but if you multiply the number by 2, that does turn out to be about the average time. I had somebody already take it in my lab, and she finished in about 50 minutes. Okay, so there's plenty of time for this exam. So, but that's really only an average of 1. I know there'll be some people that'll take longer. Don't feel bad if you need to take longer. I'm making the exam deliberately, you know, giving you extra time so you can finish up. So I was going to review some concepts. I don't know if I'll have time to go through everything because there's a little glitch here, but I want to go through the highlights. This is not going to be a comprehensive review. Your studying is going to be a comprehensive review. I'm just going to hit the high points. I do know that some of the things I'm going to talk about are on the exam, and I know there's some things that are not on the exam, so don't expect me to show you everything today in an hour. All right, so we talked about bonding. We talked about rules. We talked about rules for building neutral molecules, okay? And what are those rules? Well, we can imagine carbon, nitrogen, oxygen, hydrogen, some of the main things, and then we can lump our halogens together down here. And one of the interesting rules is for building neutral molecules, these different atoms are going to have a certain number of bonds around them. For carbon, that's 4 bonds. For nitrogen, that's 3 bonds. For oxygen, 2 bonds. Hydrogen, 1, and halogens, 1 bond, okay? And so, you know, an example of that would be our friend ethylene here. As you can see, the carbons both have 4 bonds. The hydrogens all have 1 bond. This is a neutral, uncharged molecule. Okay. Now we can draw out this ethylene in a couple of different ways. You could really write it out in abbreviated style like this. This would indicate that you have 2 carbons, and of course you could assume that you know the hydrogens are there. You could write it out like this. You could include the hydrogens explicitly if you wanted, and not include the carbons. But generally, these are all equivalent line bond notations. Okay. So the other key thing that you're going to learn about, you should know about, are functional groups. And if we had a molecule, for example, like our ethylene group, and we decided to put an R group on it, we say, you know, this is a particular functional group. There are many different types of R groups, functional groups that could be at this position. Remember, what if we had a group where, say, R was Cl? What would we have? We'd have vinyl chloride. Remember, vinyl chloride could make PVC. Well, what if we had R equal to OH? What would we have? Vinyl alcohol. Anyway, there's a variety of groups. And what are some other examples of functional groups? I heard ester. I heard acid. Alcohol. Aldehyde. What did I hear over there? Did I hear amide? No? No, probably not. Ether? Ether. Ketone. Yay, ketone. Amine. It's good. Any others? Halogens? Anyway, almost anything you think, of course, is non-carbon standard. You know, you should also know what these guys look like, right? Here's an ester. Here's an acid. Oops, Jesus. Yeah, just like that. Alcohol. Sometimes it's a little aldehyde. That's kind of tricky in this little space. Just an H instead of an OH, right? On the aldehyde. Amine. NH2. Ether. Something like that, right? You could have R1, R2, whatever you would like. Ketone. We love ketones. Wait, we have an amide. This is an amide. That's an amide. Remember, it has a carbonyl and then an NH. NH or NH2. An amide could also look like this. NH with an R group. Okay. Think of Kevlar. When you're studying, go over Kevlar and look at the amide bonds there. And amine is an NH2, and halogens, of course, are your chloride, bromine, fluorine, iodine, whatever. Okay. So those are a pretty extensive list there. We probably left out a few. So an important thing to consider when you're drawing up molecules and you're thinking about functional groups is, well, what is the formal charge of particular atoms in my molecule? And we carefully defined formal charge as equal to the number of valence electrons minus the number of, and that's the valence, electrons in that atom in isolation, minus the number of lone pair electrons, minus 1/2 the number of bonded, okay, I'll put a number sign, number of bonded electrons. So that's your formula for formal charge. If we had a molecule like our friend H3, geez. I like my other pen better because it has an eraser on it. Okay, give my pen back. If we had acetic acid here, and in the acetate form, of course this is a giveaway, but that's not the point. We have these lone pairs around these oxygens. Now one thing that should tell you, of course, that this particular oxygen I'm going to put a red box around is special. How many bonds is it making? 1. So is it going to be neutral? No. That's why you first memorize this table, or just you should just know it. There's no memory work should be involved at that point. And so the question is, okay, well, what's the formal charge on this oxygen? Now you experience organic chemistry, it's negatively charged, but I'm going to give you on the exam something you hadn't seen before, so it's not so easy, because you'll have to sit here and run a calculation. There's 6 valence electrons around an oxygen in isolation, right? On the periodic table, it's 8 right there. Hey, it's lit up. Look at that. 8 minus 2 for that orbital, right? Yeah. Okay. 6 valence in the outer shell, in the second shell. Okay. 6 valence electrons, lone pair. How many of them? 6. I just wrote it. Okay, and then 1 electron for 1/2 times the number of bonded. Okay, so the formal charge, we just abbreviate FC, is 6 minus 6 minus 1, which is equal to -1. Okay, and there you go. This is a minus. Usually people put a minus sign there, but I didn't put it there because that was the point of the problem. So that's how you compute formal charge in these. And remember, we talked about borate, for example. Formal charge doesn't exactly tell you where the charges are going to reside in a true molecular system in reality in solution. Okay, for example, that really isn't going to be, that molecule isn't going to exist in this, necessarily, and it's going to actually resonate between the two. So the two oxygens are equivalent, and those extra pair of electrons are going to oscillate between the two. We call that resonance. And so really, there's going to be a half charge on either position. But don't worry about that. When you're asked to compute formal charge, you're asked to compute it exactly on the system as drawn. Okay, but in reality, you should be thinking, more, broadly chemically about it, and you should be thinking, well, wait a second, these electrons might move here, and so there are other possible charge states for the system. So the overall true chemical charge might vary depending on the chemical system. All right, so non-covalent forces, we went through this a lot, probably several lectures. In particular, we're talking about polymers and polymer structure. And I'll do these in a different order than I lectured in, just for maybe simplest. Ionic bonds. We talked about ionic bonds. Typically people think of ionic bonds between opposite charges. Of course, that's when you have a bond. But you can also have ionic interactions. And I write interaction because this can also include these kinds of interactions. These are attractive. If I draw these force arrows, they're attractive. But if these charges are the same, in the electrostatic world, they are not attracted to one another. Okay, not necessarily in the human world, but in the chemical world, that's true. All right, and so then we have those. We have hydrogen bonds. Okay, and hydrogen bonds are an alignment of a hydrogen donor and acceptor. So guess what's involved always in a hydrogen bond? A hydrogen. That's good. You're going to pass now. Okay, so you can have a donor. I didn't even draw a donor there. You can have an acceptor, and here's a donor. And you have some lone pairs there on your oxygen, and basically this hydrogen can be shared. And I draw these vertical slashes. That's sort of how people denote that this hydrogen is shared. It's much tighter on the alcohol group. It's much closer there. That's a real bond. But it's in sort of a pseudo bond with the carbonyl oxygen. Okay, call that a hydrogen bond. Now, what's the other key concept here is that we have dipoles, right? Really, we're aligning dipoles. We have a partial positive on this end, a partial negative on this end. Sometimes we draw it like this, with a positive sign on one end, and then we draw the arrow towards the negative. That's not how it's drawn in all textbooks, but that's how we've done it in this class. And likewise, you'll have a dipole here. It's partial positive on the proton, and partial negative here. So you'll have another dipole. These dipoles are somewhat aligned. Okay, so you have a dipole-dipole interaction in a hydrogen bond. Okay, van der Waals interactions. Van der Waals. Okay, you can imagine having completely uncharged atoms, for example, some sort of noble gas, and you could have an unequal distribution of electrons in those molecules, a polarization, okay, if you will. And again, you'd end up having one side being more positively charged than the other, and there's a net attractive potential between atoms. They want to sit near each other and experience this attractive van der Waals interaction. Another way of calling this is a London dispersion force. So as I've drawn it here, of course, these are attractive. They're weaker than hydrogen bonds and much weaker than ionic bonds. Okay, this is just another name, AKA. Okay. And we talked about hydrophobic forces. Typically, some people call this a hydrophobic effect. And, we talked about a polymer that might have groups in it that are so-called hydrophobes. What's a good hydrophobe? Something like a benzene ring, something maybe like an isopropyl group, something with hydrocarbon on it. You make it really greasy if you like. Put a big, long aliphatic chain on there. Okay? And we'll just color these a color. We'll pick red. And what happens is, you'll have waters. These are waters, these little carrots here around the hydrophobes. The waters have to go everywhere. This thing's in solvent, and they form extremely ordered. These are very ordered hydrogen bonds. These are ordered waters. These are ordered hydrogen bonds. Okay, they're not very flexible. These hydrophobes. They sort of require a few different configurations. Okay, so what tends to want to happen, and you see this when you put oil into your spaghetti saucepan when you cook your pasta or whatever, that the oil goes in and it might be dispersed in a bunch of small particles. There's a lot of surface area around all those oil droplets. But what happens if you let that system relax before you turn on the heater? You want to do an experiment. Then you'll watch the oil come together like the Terminator 2, right, after it's scattered. And it will recongeal into a much larger oil blob. And what it's doing is it's minimizing surface area exposure to solvent. And that's what happens in a polymer. This polymer is going to collapse, and it's going to try to minimize solvent exposure because that is a low energy configuration. This is high energy. This is high energy because of entropy. Okay? And you're going to have a very organized system, very low entropy. And what the system's going to want to do, we draw an arrow over here, and we imagine the system forming the low energy configuration, is the hydrophobes are going to want to bunch up next to each other, and the waters are going to be excited about this because they get to be out here into bulk solvent. Now these are bulk water, and bulk water gets to change up with partners and move around, and it's happy and it's low energy, okay? Gets to occupy many configurations. Many configurations always means that delta S is going up or down. If you're increasing the number of configurations, is delta S going up? Yep, delta S is increasing, okay? The low energy state is when your closet in your dorm room is completely organized. All your shoes are next to each other. Have you ever had to lift that one shoe? Was it under the bed? In the laundry? Yeah, exactly. That is actually a high energy situation, okay? It's not very organized. The low, that's a low energy situation is when your closet is disorganized. Okay, the high energy situation is when your closet is completely organized. I said that wrong. I'm sorry. So what you're going to see here in this hydrophobic example is that the hydrophobes are going to want to come together and reduce exposure to water. The water is going to be liberated. It's going to go to high energy state, occupy many more configurations. And remember, it's minus T times delta S. And so when entropy goes up, then free energy goes down. Okay. If we assume that there's no changes in enthalpy, which we are doing here. Okay. So that's pretty good. And how about van der Waals interactions? We did some graphing, and I think it's important to review. So here's a van der Waals interaction on a nice graph we're plotting. Remember, we have some atoms that are some distance apart. Their atom centers are here, and we consider their radius, or their van der Waals radius. We'll just do the capital R here. And that's the distance between the atom centers. And we know that if these clouds overlap, and we're in this situation, this is very high energy. Okay? This is an overlap. Overlap of the E clouds, okay? Overlap of the electron clouds is high energy. This is an electrostatic phenomenon. Electrons don't like each other, don't want to be crowded out. And likewise, if these guys are really far apart, we're in this situation, and we're infinitely far apart. There's no attractive potential between them. They don't even know that each other exists. But as they're coming closer and closer together, and then eventually they're just touching, the radius, of course, is going to shorten up. And when they're just touching, and you have this nice polarization, then you'll have the most stable system here. Okay, this is the most stable configuration, and some people call this distance R0. Okay, to denote that perfect van der Waals distance. And so, I went into a little more detail in the lecture class. You don't need to know the formula or anything like that, but you need to understand the basics of this plot. Okay, so polymers. What are the two different kinds of polymers that we talked about? Polymerization mechanisms. Addition and condensation, right? Addition, we'll do that first. Addition, polymerization. Okay, so what are examples of addition polymers? I'll give you a hint. It starts with poly. Polystyrene, polyvinyl chloride, polyvinyl alcohol. Alcohol. What do these guys look like? Generally what's going on, you'll have a double bond, okay? And in that double bond, you can form a radical. You usually use a peroxide. Something like benzoyl peroxide. I don't know, here's an example of a peroxide. That's another functional group right there. That's actually, when you activate that, you'll have something like this. This is a radical, a single electron, okay? Very reactive species. They don't want to pluck an electron out of that double bond and then create, a situation like this. And that will be very reactive, and you'll get a series of reactions, because when that guy reacts with another neighboring, say, styrene molecule, it'll create another radical, and that will keep occurring until two radicals run into each other by chance and form a bond. So you'll get long chains of polymers that way. Okay, those are your addition. These guys are very stable. These are stable to hydrolysis. Okay, and that's in contrast to condensation, polymerization. What are some examples there? What did you guys work with in lab? You worked with a couple of these, right? Polyethylene terephthalate. Ooh. Ugh. Terephthalate. What's that called? PET. Number 1. Coke bottle plastic. Polylactic acid. PLA. That's the fancy Berkeley, cups that say biodegradable plastic. All right. I guess you can find those in other places in Berkeley. We talked about an interesting industrial plastic used in police protection, and very strong, bulletproof. Remember, we talked about samurai swords hypothetically being made out of Kevlar. Still not quite as strong as steel, but close. You wouldn't want to go into a real samurai match with Kevlar, but it's close. And that's a polyamide. It's a polyamide. Now, what is polylactic acid? That actually is a polyester, right? And PET's a polyester. Okay. So what's happening in condensation polymers is we're forming amide and ester bonds. When you form those bonds, what is the major byproduct? Water. Water is produced during polymerization. So that means that the reverse process is also possible. What do we call that? We call that hydrolysis. So these guys are relatively unstable to hydrolysis, of course. That Kevlar vest might be strong as steel, but if you put it in hot, say sodium hydroxide or something like this, then it's going to start to break down. Remember what you put sodium or potassium hydroxide with your PET or your polylactic acid plastic, and those guys broke down, right? The bonds were broken. Okay. All right, so the notation for polymers that we've been using, to denote a polymer, if you have something like styrene, that's a styrene, and you want to denote it, the polymer is something like this. Okay. And you put a little N there to denote many. This is polystyrene. And let's say lactic acid looks something like this. It's an acid, so it has carboxylic acid. It also has an alcohol group on the other end. So this is a condensation polymer, so you need the alcohol plus an acid to make an ester. So you would denote its structure like this in the polymer. And you're going to produce N-1. If you made N length polymer, you're going to produce N-1 water in that polymerization reaction. Okay, and we call this PLA, polylactic acid. All right, so that, I'm sorry, it's probably kind of an abbreviated, quickie polymer thing here. Oh. So equilibria, we talked about